Bismillahirrahmanirrahim. So just before we move on to the next part, which is the last part of this topic, I would just like to emphasize on what the numbers indicate. Okay, so hold on. Okay, right. Looking at the first example, 9.1, where we have a system, the solvents are aqueous, water, and the other layer is the organic solvent, and our solute is ammonia. So if our expression of KPC is concentration of ammonia in organic layer over the concentration of ammonia in aqueous, this number, the KPC number, can actually tell you about the relative solubility, whether your ammonia is more soluble in organic layer or it's more soluble in aqueous layer. So if you look at the number 0.28, you can see that it's a small number, less than 1. So the bottom number is bigger than the top number. Do you all agree? In terms of mathematically, in general, yeah? So that means the bottom number is a big number. So ammonia is more soluble in aqueous, in water. Okay? Another example that we were doing is example 9.2. Same thing. Our system, our solute is BDA, and then our solvents are aqueous and ether. So if we want to know if BDA is more soluble in ether or in water, which is your aqueous layer, you look at the number. 0.156 is again smaller than 1. So if you look at the expression, a number that is smaller than 1 would indicate the bottom number is bigger than the top one. Okay, so that means the concentration of BDA in aqueous is higher, which suggests BDA is more soluble in aqueous solvent compared to in ether. All right. Furthermore, this is also the same. Okay, it's smaller than 1, which suggests the bottom number is bigger, so Q must mean that it is more soluble in hexane than in methanol. Q must be able to dissolve in both layers in order for it to move between the layers, okay? But it's just, if we talk about the relative solubility, looking at the number, it will be more soluble in hexane, okay? So for those of you who just joined, can you please switch on your camera? Thank you, except for Yadi who said, wait. This example 9.4, you can see that the number is 2.81. Now it's bigger than 1. So this suggests the top number of the KPC expression is higher than the bottom number, right? Which implies that J is more soluble in ETH, ethoxyethane, than it is in water. Are we all okay so far? Okay. So that brings us to the next part, the factors that affect partition coefficient, okay? What are the factors that influence the number that we are looking at? So we will be looking at it in terms of polarities of the solute and solvent. If you remember the polar and non-polar characteristic of a molecule, this is from your AS syllabus topic 3, okay? So I remember telling you in AS, polar molecule will dissolve in a polar solvent. So polar dissolve in polar, non-polar dissolve in non-polar. Still remember this? Okay, the reason for that is because there is an interaction. There is actually an intermolecular force between these two molecules. If they dissolve or if we say that a solute is soluble in this particular solvent, that means there must be an intermolecular force forming between the solute and the solvent. So that's what we're going to look at in the next slide. Okay, so what KPC can tell us is the solubilities, relative solubilities between the two solvents. Okay, your solid must be able to dissolve in both layers. The degree of solubility is determined by the strength of the intermolecular bonds, or I think we're more familiar with the term intermolecular force. This depends on the polarity of the solid and solvent molecules. So whether they are polar versus non-polar. Okay, just to remind you, polar molecules are a molecule that has its dipoles cancel out. Okay, dipoles is the delta plus and delta minus. Polar molecule is for molecules that the dipoles don't cancel out. So we're going to look at the next example, ammonia. Okay, so if you remember ammonia and how we look at the polarity, the nitrogen is delta minus and all hydrogen have delta plus. The presence of lone pair suggests that ammonia is a polar molecule. Okay, so we want to look at ammonia in water, H2O. Again, there is a lone pair which suggests H2O to be also a polar molecule. Okay, the other solvent is carbon tetrachloride, CCl4. So CCl4 will be a tetrahedral. So this is just a little bit of revision from your AS syllabus. Now, even though each bond is a polar bond, but because there is a symmetry in the molecule, overall, they become nonpolar. Okay, so ammonia is soluble in both, but at a different extent. Okay, so when ammonia is in water, it's a polar-polar interaction. Now for AS syllabus, it's enough for you to know, oh, polar will dissolve in polar solvents. But in A2, you have to know what is the type of interaction. Okay, if you remember NH and OH, there's a special intermolecular force between this that can happen. Okay, it's called the hydrogen bond, where F, O, and N. So you've got a nitrogen attached to hydrogen, and you've got an oxygen attached to hydrogen. So between ammonia and water, hydrogen bond can form. Okay, whereas ammonia, which is a nonpolar, ammonia, which is a polar, and CCl4, which is nonpolar. So usually polar molecule, if you remember, would have permanent dipole, okay, for the ammonia. But since CCl4 is nonpolar, and usually nonpolar is instantaneous dipole, induced dipole. Yes, remember? So since we have a combination of polar and nonpolar, we call that interaction as permanent dipole, induced dipole. So the permanent dipole comes from the ammonia being polar, and the induced dipole comes from the CCl4 being nonpolar. We already know that for intermolecular forces, hydrogen bond is the strongest. Therefore, ammonia is most soluble in water. Or if we're talking about relative, it is more soluble in water than it is in CCl4. That is how you determine or explain your KPC values, okay? So here, ammonia and water are both polar molecules that form hydrogen bond. Okay, so we've already looked at this. Ammonia form permanent dipole induced dipole forces with the nonpolar CCl4. Since these forces are much weaker than hydrogen bonding, ammonia is less soluble in CCl4. Okay, is everyone okay with this? Can follow? Okay, right. So if you want to copy this down, you can, but everything is already explained in words. And I believe that is, no, we have one more slide. The last section of this topic is basically talking about what I started with at the start of the lesson just now. When your KPC is smaller than 1, that means you have to look at your expression. Okay, the bottom number is bigger, and usually we put our aqueous solvent to be the bottom layer, and anything other than aqueous, like organic layer, whether it's ethoxyethane, whether it's hexane or benzene, then it will form the top layer. Okay, so the explanation this, I have gone through it at the start of this lesson just now. Now, we are done with topic 25, but before we close this topic, I would like to have a look at one question from the exercise. I believe it is, if you take out your exercise 25.1, if I'm not mistaken, it is question 28. Oops, question 28. Okay, so we'll do question 28. I've prepared the drawing earlier. You can have a read first at the question. Nina, okay kaya siya dia? I don't know what.
Cakap ia takut.
Why? What is he scared of? Oh my God. You see here, Rooney is here, Tarmizi is here, Ridwan is here, Danish is here. What, he's scared that we're going to use his photo, is it?
Huh? Entah. And he asked me apa tu. I said no one looking with and then he said cannot see kan. I said no. And now he said shush.
Yeah, we cannot see you, Yadi. Only I can see
Sorry,
you.
Yadi.
And then Yadi was like, I don't want to text Nina next time because she tells Miss what I text her. Okay. Right. Question 28. Yadi, I hope you are also doing it now, even though I cannot see you. Tomorrow you must switch on your camera, okay? Because it's APR. You cannot switch off your camera. Oh, there we go. We have Yadi here. Okay. Right. So question 28, when 100 centimeter cube of an aqueous solution. So that means aqueous is your solvent. And I just said it just now. Usually I tend to put the aqueous layer at the bottom. Okay. So I'll just highlight that. And then containing 0.5 grams of organic compound X. So our solute here is solute X, shaken with 20 centimeter cube of hexane. So then my hexane goes to the top. All right. This is initial. I have only prepared the initial drawing, but no problem. If you want to do the initial and then at equilibrium is also fine. Paste. But of course, at equilibrium, so initial at equilibrium or after shaking, okay, it's the same thing. We still have the same volume, except this time the mass is no longer 0.50 grams, okay? It will be something else. And some of my solute have also moved into the hexane layer, right? Calculate the partition coefficient of X between hexane and, it was found that 0.40 grams of X was extracted. So that means at equilibrium, we have 0.40. Okay, so that means if we know how much mass of solute we started with, and we know how much have gone into hexane, we can find the mass of solute in aqueous layer. Okay, so I've already prepared the diagram for you, and I've also given you hints there. You can quickly work it out. So this is the concentration, if you're wondering what that is, okay? Oh yeah, I just remembered yesterday, I was corrected in one of the example. Have you changed? Have you changed the mistake that I made? So make sure you change it, okay? I got it the other way around. So you have to follow your expression. If it's hexane on top, that means I need to take the concentration of hexane. In this case, my concentration is in terms of mass over volume, which is gram per cm cube. Okay, so just make sure that it's the correct mass of hexane and the correct volume of hexane. And for the bottom number, it's the mass of X in aqueous over the volume of aqueous. Okay, so this part, I think you already know why I did that, because to find the mass of solute in the aqueous solution, you take the initial minus mass of solute in hexane. So I've got 12 today, full attendance. Okay. Yadi, you're the answer. Usually you're the first one to find the answer. Alicia, do you have the answer? She's shy now. Apa kan Yadi? I cannot see. What's the answer? Yes, Yadi, what's the answer?
20.
Yes, thank you. The answer is 20 and there is no units. Okay, let me just make sure that everyone managed to get that answer. Just nod your head if you got it as 20. Okay, okay, Ridwan is giving me a thumbs up, thank you. Kohwi, okay, very, okay, right. Thank you, everyone. Now, the next part of the question, the instruction is short, but actually the process is long, okay? So let me just recap. Just now we started with 100 centimeter cube of water and also 20 centimeter cube of hexane. And then we managed to extract 0.040 grams of X into hexane, okay? Extract means we managed to dissolve 0.40 grams of X into the hexane layer. Now, if two 10 centimeter cube portion, that means 2 times 10 centimeter cube of hexane. Okay, were used instead of a single 20 centimeter cube portion. So they're now trying to do the same extraction, but the first one, you do it in one step, in one go, with 20 centimeter cube of hexane. But in the second part of the question, you want to do in 2 steps where you first use 10 centimeter cube of hexane for the first extraction or the first shaking, and then you use another 10 centimeter cube of hexane in the second extraction or in the second washing. Okay, so what they want you to do is to compare the amount of X extracted. Now, this part number 3, it doesn't say the amount of X extracted in which layer. Is it in the aqueous layer or in the hexane layer? But luckily, in the first part, it says that X was extracted into the hexane. So that means we are interested to know the total of X in the hexane layer when we add the first 10 centimeter cube of hexane with the second centimeter cube of hexane. So that means it's not directly mentioned here, but the fact that it says 210 centimeter cube portion means you have to do the shaking or extraction in 2 steps for 2 times. Okay, so let's just go through that quickly. I will explain while you can start copying down the diagram. So initially, you're going to start with the same volume of water layer or aqueous layer, which is 100 centimeter cube. And you also use the same mass, initial mass, which is 0.50 grams. The only difference this time is we are using 10 centimeter cube of hexane first. So after shaking, I should have some of my solute X moving to my hexane layer, but I don't know how much. Okay, so that is the question. How many grams of X in aqueous and how many grams of X in hexane? I don't know. And then I separate them. See, this is the part where students always get stuck because it is not explicitly mentioned in the question that you are to separate them after the first extraction, and then you will use a fresh new sample of hexane, 10 centimeter cube, okay, to be added to the remaining aqueous layer. You do not use a new aqueous layer. You use aqueous layer from the first shaking. Is that okay? Okay. And then of course, initially now I use green color so that you know that the hexane is a new sample, a fresh hexane, and initially there wouldn't be any solute X in that new hexane layer. Only after shaking, I should see some of my solute X moving into that layer. Okay, I do not have any numbers. I don't know how much of X I have in the aqueous layer. Sorry, not that one. Oh, that one I also don't know. And I don't know how much of X in hexane after the second shaking or the second extraction. What I do know is that because the system is the same solvents, hexane and water, same solute, the only thing that's constant is the KPC, which is equals to 20. Okay, so the expression of my KPC should be the same. Concentration of X hexane is equals to the concentration of X in aqueous. So I'll just move this, all right? But we don't know anything about the mass of the solute in aqueous or in hexane, and we cannot assume that because our volume is half, the mass is also half. No, we cannot assume that, all right? So what we can do is, again, let mass, so this is for the first extraction, okay? Let mass of X in hexane to be, I wouldn't call it X, say Y, okay? So if the mass of X in hexane is Y, what is the mass of X in aqueous? What do you think? Can anyone suggest if mass of X in hexane is Y, how do I find the mass of X in aqueous layer? Anyone would like to try answering? There are two unknowns here, but I know that the total of X in aqueous plus the total of X in hexane is equals to my initial mass, which is 0.50 grams. So how do I write the mass of X in aqueous? Anyone? Apple, would you like to try?
0.5 minus y.
Yes, correct. Thank you. It's 0.5 minus y. Okay, so it's a bit confusing because our solute is X and then we use unknown y. Okay, so I can add another concentration of X in hexane would be y over 10. The concentration of X in aqueous would be 0.5 minus y over the volume, which is 100. So if you're wondering what this is, it is mass over volume. Okay. And then you just sub in the expression y over 10 divide by, which turns out to be times 100 over 0.5 minus y equals to 20. So here is a short maths class for you to work out, to solve what y is. If you're wondering why I suddenly got an x, it's because I just divide the concentration and then I turn it into a multiplication. Okay, I don't know if you are comfortable with that. If you are not, then I will add another line there where y over 10 is equal, will be divided by 0.5 minus y over 100, which is equals to 20.
Miss,
Yes?
the screen is stuck.
Oh,
Freeze.
the screen is stuck.
Yeah,
Thank
for
you.
me and Iwe.
Oh,
And
okay,
Miss.
okay. How long has it been stuck?
5 minutes.
Huh? 5 minutes and you guys didn't tell me? Oh my. Hold on. Oh gosh. Okay, let's see. This one. When did it get stuck? This whole orange font.
Yes.
Okay, bah. But you guys can follow what I was saying just now. Yeah? All right. So I will thank you for letting me know. 5 minutes later, Yadi's just laughing. So I'll let you work out what y is first, and then we'll move on to the next part, which is the second extraction or the second shaking. I zoom out a little bit, just in case you want to copy the whole thing together with the diagram. We have an answer from Ridwan, but he doesn't want to say out the answer. Let me check. Thank you, Ridwan. The answer is yes, correct. Y is 0.33. So if we go back to what Y is, that is the mass of hexane. So I can update my diagram. The mass of hexane is 0.33 grams. So that means I also have 0.33 grams here after separating the layers. To find the mass of aqueous, I will have to take 0.5 minus 0.33, which is 0.17. Did you all manage to get 0.33? Okay, so if you didn't get 0.33, maybe there's a mathematical error, okay, in your working. Please let me know if you're ready to move on to the next one. Okay. So, after the first washing, it was then separated. Okay, we're going to use the same aqueous layer. That means in that aqueous layer, I have 0.17 grams of X, right? And I don't know how much there is in hexane. This time I'm going to use my second 10 centimeter cube of hexane. All right. So this is what it means by 2 times 10 centimeter cubes of hexane. Okay, we're going to use a fresh sample, which initially you will not have any solute X in this layer. Okay, and then you will do second shaking, then only you see some of the solute molecules moving to that layer. And again, I know the initial, sorry, this is not question mark. This is just 0. Initially, there's no X in that layer. Okay, so next part, the second shaking, I started with 0.17 grams. Okay, because that's what I have left from my first washing. Okay, again, I do not know the masses in each layer, but I do know that the system is still the same. Same hexane, same aqueous, and same solute. And the only thing that is constant for this system is the KPC. KPC is equals to 20 hexane over aqueous. Okay. Again, we don't know the masses, so we are going to introduce another unknown. Let mass of X in hexane to be Z this time for the second washing. Okay. So mass of X in aqueous would be, what's the mass of X in aqueous? Anyone wants to answer? Someone whose voice I haven't heard? What is the mass of X in aqueous? We is like, sorry?
0.5 minus Z.
0.5. Okay. What's our starting mass for the second shaking? What did we start with?
0.17.
0.17 minus Z. Yes, correct. Okay, thank you. 0.17 minus Z. So you have to be careful there, yeah? So it's easy to think that our starting is 0.5, but that 0.5 has already been distributed and 0.33 has been separated. So we're only left with 0.17. So same thing, you would solve. I don't need to show you. The concentration of hexane this time would be Z over 10 divided by 0.17 minus Z over 100 equals to 20. Okay, so you can work out Z. Okay. Answer, Ridwan, you have an answer? Is Ridwan still here? Yes. I see half of his face. Ridwan had the answer already?
0.113.
Yes, thank you. 0.113 grams. Okay, so then I will fill in. So now I have 0.113 grams. I'm actually not interested in the aqueous pulang, really, because the question says, calculate the total amount of X extracted. If in the future you're wondering extracted where, extracted in hexane. So the total mass of X in hexane would be, let me highlight it, this one, 0.33 grams plus 0.113 grams. So that should come out as 0.443 grams. Okay. Okay, so if you notice between these two processes, they have the same total volume. Yeah, they use 20 centimeter cube of hexane in total, 100 centimeter cube of water, and also they started with the same mass, 0.50 grams. Can you spot that? Yeah, all the information are the same, except that for the second part, they break down or they divide it into two steps. Okay, so you can see for the first part, they managed to get 0.4 grams of X. And the second part, we managed to calculate 0.443 grams. So the mass is bigger, right? If you were to extract the solute in many steps, okay? So it is better to do many steps, but with smaller volume, okay? Provided that the total volume is the same. In the end, they use 20 centimeter cube of hexane for both, all right? But the only difference is the number of times they shake it. So the more times you mix or shake, the bigger the mass will be, right? And then they say to compare this with the amount extracted, they will say that the difference in 0.443 minus 0.40. There's a difference in 0.043 grams. Okay, so if you want to comment, difference in 0.443 grams. All right, so that is done. I just want to go through quickly, okay, for the pre-APR test that I have not touched. But I have already uploaded the mark scheme. So if you want to revise or you want to check if what you did in the test was correct or not, some of your papers are with me. Some of you guys did it at home, so you can always check your answer. But they are the mark scheme is available anyway for you. Okay, so let's have a look. Not this one. It is this one. Okay. So the first question, question 1, calculate the lattice energy of silver bromide. Now, if they don't specify you to draw the Born-Haber cycle, the quickest way is, of course, to first start with your formula. Okay, lattice is equals to F minus delta H1, right? Some of you don't have your papers, that's fine. You can always refer to this document later on and just follow through my explanation. Okay, so silver bromide solid is made up of silver ion and bromide ion, Ag plus and Br minus. Okay, so your goal is to start. So if to calculate delta H1 is this whole thing, this whole process that I will include, is to start with your elements in its standard state. Silver is a solid. Bromine is a Br2 liquid. Okay, your endpoint would have to be Ag plus gas and Br minus gas. Now you have to be careful here because you started with Br2 and in the end you only want a single atom. Okay, so let's start with silver first. First, you have to convert the solid into a gas. So that's atomization of silver. Okay, and then you want to convert your silver ion to silver plus gas, and that's your first ionization energy of silver. Okay, so first IE. You're done, right? You've already reached your endpoint. So I will just erase that, Ag plus. So whatever the number is here, you just add them all up together with your bromine, which we will look at shortly. Bromine, Br2, you only want a single atom in gas state. So that means we have to half the Br2 to produce one bromine atom. And this is atomization of bromine. Now, you do not have to divide it by 2 because by definition, atomization of bromine is the formation of 1 mole. Okay, and then you want to convert the bromine into an anion that is the electron affinity EA1, electron affinity of bromine, okay, which is given. So all this, you just have to add them up, and that is your delta H1, and you sub it into the expression. Okay, so I'll just teach you how to do that quickly, and then for revision later on, you can work it out. These are all explanation and definition, so I will not touch that. For this question, question 2 part C, I think it's question 2 part C. Yeah, question 2 part C is also something that we have discussed in the class. Okay, it's exactly the same question as in your exercise. So I will just leave the working there. I think it should be self-explanatory. So to find the enthalpy change of solution of magnesium chloride, I just need to arrange delta HF here of magnesium chloride aqueous and delta HF of magnesium chloride solid. Okay, and then you work it out later. So okay, question 3 is what I want to point out to you, because since your syllabus, you will not be given a data booklet, you will be given a list of things that you may not have to use everything. Okay, that is Cambridge's way of tricking you into thinking, oh, I have to use all these numbers. Okay, but actually no need. So we want to find potassium oxide. Lattice energy of potassium oxide is K2O, which is made up of 2K plus and O2 minus. To find lattice energy, delta H lattice is delta HF minus delta H1. And delta H1 is the one that we want to find first. Remember, you want to end with, let's start with K plus to look, okay? K plus gas and O2 minus gas, starting with elements in its standard state. O2 gas, okay? So these are your elements in standard state. Okay, so as usual, your potassium is a metal solid. We need to convert it into a gaseous atom, and that is atomization of potassium. Okay, I've already highlighted that for you in blue. After turning the potassium into a gaseous atom, you want to form the cation, okay, which is actually just first IE of potassium here. You notice that they also give you the second ionization energy. That is only to trick you. You do not need it. You do not have to use it because you only stop at first ionization energy. Okay. Now, bear in mind that you need 2 lots of potassium plus. So that means everything must be multiplied by 2. Okay? Do you all agree? Next is the oxygen. O2, you want to break it into a single oxygen atom. And if you draw out oxygen, it contains a double bond. You see here, you are given bond energy O double bond O and O single bond O. The correct one is to choose the double bond because oxygen molecule contains the double bond. So if I break it, I form 2 oxygen gaseous atom, but I only need 1. So that's why I have to divide it by 2. So half of bond energy O double bond O. Next, I want to turn my oxygen into an anion, O minus gas. That is represented by the first electron affinity, which is this one. Okay. And the second electron affinity is the electron affinity of O minus. I'll just write down the numbers so you don't get confused. Negative 141 and positive 798. Okay, and then you're done. You get O2 minus. So all this is again delta H1. After you add up all your delta H1, you will then use the expression. Okay, so I will let you work that out yourself later on. Just the last one that I would like to touch on, so then I don't have to go back later when we do correction. Okay. Okay. Next is question 4. Again, question 4, they give you, because you don't have a data booklet, so they will give you a list of values, but you have to be, sometimes you have to spot and do this very quickly, because I am sure when you're in an exam or a test, you will be under a lot of pressure. You may think, oh, I have to use all these numbers. Okay, actually, you don't need all those numbers. They say these are the values for radium sulfide, RAS, which is made up of Ra2 plus and S2 minus. Now, so you will be tempted to think that, okay, I need to start with Ra solid and then end with Ra2 minus gas, and sulfur, I need to start with S8. I need to highlight that sulfur exists as S8 molecules, okay? And then the endpoint is S2 minus, okay? And you will be tempted to work all these steps, but actually you do not need this at all. You just need to work on the sulfur. Okay, let's see. If I want to break or to atomize my S8 molecule, I will get 8 sulfur. Agree? But in the end, I only need 1. So what must I do? I divide by 8. Everyone agree? Okay, so that means my atomization here is, I don't know the atomization. It's not given. Okay, so I will just write down X for now. Because manadakan atomization of sulfur. Okay, next. After, I'm going to erase this 8/8 because that's just 1 sulfur. Agree? 1 atom. And then I want to turn my sulfur atom into S minus. And that is first electron affinity of sulfur. I'm adding electron to sulfur, minus 200. And then second electron affinity is plus 532. Okay. Now, can you see this? Enthalpy change for 1/8 S8 to form S2 minus is 555. 1/8 S8 to form S2 minus is 555 kilojoules per mole. That means the process of this whole thing is 555 kilojoules per mole. So you're asking, okay, where are we going for this? We want to find this, which is 8 times of the atomization of sulfur. Okay, so from here, we can say that 555 is equals to X plus negative 200 plus 532. Okay. That should come out as 223. Did you all get 223? Okay. Or maybe some of you Don't have the paper. Okay. Now, this x is, if you go back to upper exane, is 1 over 8 S8 to go to S. How do I find? Okay, and the process for this is 2 to 3. The question wants me to find, sorry, it is not gas, it should be solid. The question wants me to find what is the enthalpy change when S8 is atomized into 8 sulfur atom. How do you think these two are related? Would anyone like to answer? How can I use 2 to 3 to answer what the question is asking for? This is actually atomization. Sorry, yes?
Times 8.
Yes, correct. Times by 8. Okay, so my x at the moment is the atomization of sulfur, but the question is asking about something else, not the atomization of sulfur. So to answer what the question wants, it has to be this one, salah. This whole thing times by 8. So that means it's 2 to 3 times by 8. Okay, so this is first time I think I've seen question in this format. And I don't remember if a similar question will appear in your APR. I think not, but this is definitely a question from your latest syllabus. So you need to know how to do it. Okay. Right. So if you're still like, you know, still not getting it, I suggest you to try out the questions again and then refer to the mark scheme. Okay. I think that's all the questions that I want to discuss because everything else is quite self-explanatory. If you have a question, you can always ask me. Preferably in the afternoon lah. Don't start asking me at like 1 in the morning or like 4 in the morning, just few hours before your test. Okay, so please make sure you try the exercise, the questions, refer to the mark scheme. Don't just do it by looking because these are numbers, right? So you can always do it quickly by putting in the numbers into the calculator, but also learn the explanation. Okay, explanation like relative sizes. Why is the lattice energy for this bigger than the other? Or why is the hydration energy this amount compared to the other? What you do not need to learn about is ion polarization. Okay, to explain why the thermal decomposition or the thermal stability increases as you go down the group. Okay, that one, I think, if I'm not mistaken, it's page, let me just confirm it, page 8 and 9 of your notes. Let me just double check. Yes, page 8 and 9 in your textbook. You don't, not textbook, sorry. In your notes, you don't have to learn for tomorrow's test. Okay? Do you have any questions before we go? No? Okay. In that case, be prepared for your test tomorrow. Don't forget to go through the checklist and all the things I have listed down. Hopefully everything will go smoothly tomorrow. Hopefully no blackout or anything. Internet connection also okay. And hopefully the school doesn't reopen suddenly tomorrow. But so far, nada pulang. So we should be able to do our APR at home in peace, but also with your camera on. Okay? All right, then. Thank you, everyone. Assalamualaikum.
Waalaikumsalam. Thank you,
Thank you,
Miss.
Miss.
You're welcome. Bye.
Thank you, Miss.
Miss. Thank you,
You're
Miss.
welcome. You're welcome.